Hi. I mean, we just had a snack, but this isn't a snack one. Although this is still fun to watch. Go ahead. We're gonna get ready. We're gonna write down our observations. I'm just gonna hit play. Yeah, I just had to go back and look. Liquid nitrogen boils at 77 Kelvin at room pressure, so I thought that was worth writing down. Negative 200 Celsius. I got those flipped. So yeah, same as before. Same process. For these, I want to go through amount of gas, temperature, volume, and pressure. The balloon was sealed. They were tied off balloon animals. I don't think any gas went in or out of the container because if the balloons lost gas, then they wouldn't have come back to their original shape. So that one's going to be a constant. The temperature, well, liquid nitrogen, right? Liquid nitrogen's at negative 200 Celsius, and I'm pretty sure that the scientist, was in a room temperature room of about 20 to 25 Celsius. So I'd say the temperature was highly variable, and that we'll call that our independent variable. And then in response, the volume changed. So that'll be our dependent variable. It got smaller, and then when it heated back up to room temperature, it got larger again. Um, just to be clear on this image, I'm going to pause it. This flask is open right here. Oh, I can't circle. It's an open container. The balloons went in and out easily without it being sealed. So in this case, the pressure is a constant because it's taking place in the same room over this time frame. So interestingly, we've got a different set of variables, different set of constants, but we're going to go through the same process. Can we come up with a relationship between them? And I think we can. Let's try and do the same process. Yeah. Let's write it now instead of waiting till the next one, right? As temperature blank, volume blank. Well, we saw as temperature went down, volume went down, and then as temperature went back up later, the volume then went back up. The balloons reinflated almost as soon as they came out of the liquid nitrogen. And looking at this from a macroscopic scale, this could make sense. How does the lower temperature affect the particles? Well, we know that temperature is average kinetic energy. And so at a low temperature, they move slow. At a high temperature, they move fast. And as long as you have this container that can move, this piston that can move up and down, and you're not adding or removing any pressure, the volume is allowed to change. And so faster particles will take up more space and slower particles will take up less space. You can imagine if you just said all particles move half as fast, all of a sudden, they just wouldn't get very far in the same time frame. So the frequency of the collision is what we're going to look at as contributing to size in this case, which means that based on what we wrote on the previous slide, now the arrows are pointing in the same direction. As one goes up, the other goes up. As one goes down, the other goes down. This means that this one is a direct relationship for this gas. Again, the question is, can either variable be zero? Well, I don't know. It's hard to say. Like, the temperature went negative. Actually, hold on. Much better. Sorry, bad scientist. Temperature almost always goes on the x-axis. Temperature went negative. So the question is, like, can we get around that? I'm going to extend that line really quick because we had a situation where we were at, say, 20 Celsius, and then we cooled it down to negative 200. And so our volume temperature graph would look something like this, I guess. As one goes up, the other goes up. Direct relationship. Right now we have a positive slope. But can either variable be zero? Well, we established that it's not really possible for volume to go negative. That can't happen. Not allowed here. So if this volume were to keep going down, eventually it would hit a temperature where the volume would be zero. So really quickly, I just want to shift that over. Or I guess shift that over. And let's just define zero temperature as the temperature where volume would be zero and draw the same line. It turns out that the two graphs would look exactly the same. They're just shifted left and right. Because the two graphs have the same slope, the temperature scales are very similar in their relative size and just different in their absolute size. We've heard of this before. This is what the graph looks like if the temperature is given in Celsius, and this is what the graph looks like when the temperature is given in Kelvin. Now, I don't know about you. I personally would rather look at the Kelvin graph. I like the idea of a y-intercept of 0. And to be fair, we should talk about y-intercepts in a little bit of algebra. Just to be clear, we've got this relationship where if it's a straight line, we can write a formula, y equals mx plus b. Except to rewrite it, if we've got our y and our x as volume and temperature, v equals mt. And if we pick the Kelvin one, where the y-intercept is 0, then the b goes away. And m is just the slope of the line, and the slope is always a constant. So you know what? Let's not do m. Let's instead do k. So we're going to use that in a second, but here's the data for these two graphs. I like these two graphs. I wanted to show them. The lines that we saw before, we saw for Boyle's law that we only saw one line. If we had different samples of gas or different temperatures, you'd have other graphs that look very similar, just a little bit different. And I wanted to show what those differences would look like here. Here we've got 5 different samples of gas, and you can see on the left we graphed it in Celsius, and on the right we graphed it in Kelvin. And you can see at the bottom, each sample of gas contains a different number of moles to spread out the lines. You'll see that each one has a different slope, but of particular note, they converge at this 0 point. Now this 0 point, as I said, would be the lowest temperature. This would be the temperature where volume is 0. Volume is never 0 for a gas because a gas has particles, and those particles take up space. But I guess there's a point where the particles get really close together and then things fall apart. But up until that point, this line looks really good. The hypothetical point where all the lines converge is called absolute 0. It has plenty of other definitions and plenty of other ramifications, but it is this lowest temperature possible by the rules of our universe. We can't get there. It is physically impossible for us to engineer a machine that will get us there. It's not an eventual thing. It is actually impossible. I don't have the proof for it. I can try and find one later if you're really that interested. But we know where it is because if you have all these solid lines, you can draw these dotted lines back to where 0 would be, and you always get this same answer. We define 0 Kelvin as absolute 0, and that's negative 273.15 Celsius. That's where that formula comes from. So now bringing it back to the actual data, I think if we multiplied these, we would not get a constant. 0.7 times 100 is 70. 1.7 times 200 is 340. So we're not getting the same answer. But I think instead, if we take a look at this equation that we have here and we try and isolate the constant, K equals V over T. This would suggest that the volume divided by the temperature at any given point is a constant. And 100 divided by 0.7. Does this work? Oh no, sorry, it should be the other way around. So what's interesting with this actual real world data is that when you do divide it out, you'll see that you don't get the same number. And that's more what I was talking about before, where as the temperature goes up and you get up into these, reasonable real world temperatures as seen here, starting at about 0 and going up, the data does start looking a lot better. But we'll talk about the realistic data later. Let's just kind of use this mathematical approximation for now. Let's not get too worried about the details, and let's just get the general picture first. Speaking of general pictures, here's your law. This one's named after a different British scientist named Charles. His last name was Charles. I know that's confusing. But Charles's law says that as volume increases, temperature increases. Volume and temperature are directly proportional at constant pressure and amount of gas. Just to be clear, we had Boyle's law where it said PV equals K, and we have Charles's law that says V over T equals K. Not necessarily the same K, different Ks. But just to be clear with this, it seems like for direct relationships you divide, and for indirect relationships you multiply. I think it's worth holding on to that. But again, we're going to go through the process of doing a couple practice problems. To be clear, based on these graphs, this relationship only really works. This hinges upon temperature being in Kelvin. Otherwise, if you use it in Celsius, you have a y-intercept, and so the mathematical relationship changes and you're going to have to do a lot more algebra. So we, as a rule, will say for gas laws, temperature in Kelvin. Always, always. And if that means you have to convert, the reference table link is above my head. So let's go through. We've got our variables pulled right out. Kelvin is temperature, liters is volume. So let's write it out. I don't know if you are the cross-multiplying type. However you want to solve this is completely up to you. But if you do go through this, you will get 30 liters as your final answer. And again, that makes sense. As volume goes down, as temperature goes down, volume goes down. The same relationship that we saw before with Boyle's law, we can now say if we're in Kelvin. If the temperature doubles, the volume doubles. If the temperature is cut in half, the volume is cut in half. And that is what happened here. If you wanted to short the math, this is a 1/2, which means this has to be a 1/2. So let's take a look at the next one. If you want to do it on your own, you can. Go ahead and pause me so that you can get to your answer before I do. This time we're looking for the temperature, but I'm going to change color. This temperature is in Celsius, so we can't use that. So T1 is 10 degrees Celsius, but we're going to convert that into Kelvin. Temperature is Kelvin is Celsius plus 273. So this is going to be 283 Kelvin. Same equation as before. We're just going to pull that down. And our volume is 25.0 liters, and we're at 283 Kelvin. And 60 liters over temperature 2. It doesn't say what units for temperature, so let's start by doing some, again, if you're cross multiplier to solve, don't forget when it's in the denominator, things get a little bit more dicey. But when you do solve this out, you get 679 Kelvin. If they asked for it in Celsius, you could convert that. You just subtract back your 273, and that gives you 406 degrees Celsius. So it's really important to walk out of here thinking temperature in Kelvin, temperature in Kelvin. Note that the temperature for this problem, the volume went from 25 to 60, so it's a little over double. The Celsius temperature went from 10 to 400. That's not double. That's not a little more than double. That's a lot more than double. The law is only valid if you're using Kelvin temperature. Thanks for watching.